Yes, hello. My name is Christian Kempe. I work in Alfa Laval in Lund with heat exchanger as a product application specialist. I come here this afternoon to talk about extreme low charge refrigerant system with ammonia. And if you are here in this Chilventa days today, I think you know most about the refrigeration systems. It's about keeping things cold, occasionally hot, using some sort of a refrigeration system. And I mean, that's pretty straightforward. We have two heat exchangers, we have a compressor, expansion valve, basic components. But what runs inside that can be a little bit problematic. And that really is the refrigerant. Because the history of refrigeration has pretty much been the history of our refrigerants. I mean, that's what brings us to the news sometimes. And in the industry, we have been very good in coming up with good fluids as refrigerants. We had the CFCs, the HCFCs, good refrigerants as such, work perfectly, but they come with some side effect. They had a high ozone depletion potential, so we phased them out in the Montreal Protocol, replacing them by the HFC, which we phase out because they have a too high greenhouse warming potential. And when we phase out them, well, we go over to the HFOs, which we are now about to phase out really before we are phasing them in. So yeah, we are being quite good in switching refrigerant. And if I just have a little bit of an outlook, I would say that if the world as a total had been just as good as switching from a coal-based economy to a green economy as we had been in switching refrigerant within the refrigeration business, then this greenhouse warming potential, that would have been solved in 5 years back. But yeah, anyway, there are some constants here, and that is the natural refrigerants. More or less no ozone depletion potential, no greenhouse warming potential, more or less. But yeah, there are some side effects here as well. We all know that propane is flammable, CO2 only works under high pressure, and ammonia is toxic. But before really phasing these things out, maybe we should have a look at how dangerous are these things actually. And of course that depends case by case, but just to go back a little bit in time, I would like to refer to this report made by the Swedish Defense Research Agency. They were investigating how hazardous is an ice hockey arena with ammonia. And there are approximately 360 ice arenas just in Sweden. Some of them will see like 1,000 of spectators every week. So this is a relevant topic for the report. And what they did here was that they looked into two different systems. One with an evaporative air-cooled condenser, 600 kilowatt charge. And the other one was an indirect system with 60 kilograms of charge, all the ammonia in the machine room. What they say here is that we get a fatal leak. All the ammonia goes out at once. Not really plausible that will happen, but that's what we say in the report here. And then we categorize the risk area for the 600 kilogram system as 100 to 200 meters. The risk area is where 5% of the population need immediately hospital care. So that's quite a big distance then downward. If we look at the indirect system with 60 kilogram charge, then the machine room is defined as, the risk area is defined as the machine room. And basically we don't want to be in a machine room where we are R32 or CO2 leak either. So actually placing it in the machine room, then we are pretty safe for the public at least. And even the Swedish government authority realized this one and the importance of a low charge system. One can then ask, what is the low charge system? And there has been tons of reports written on that one. Either we can define this as the amount of charge that we have, and that is of course of interest because, I mean, the charge is what makes it more or less dangerous. Or we can look into the charge per kilowatt, grams per kilowatt, and that tells you basically, I mean, how good have we been in designing that system? However, I don't really think that this is what we should go too much into because, what's more interesting, how should we design the systems? Traditionally, in refrigeration and large cold storage, we have gone with something like this, a very direct system, pumping around a lot of ammonia, and well, it's possibly efficient. However, not from a charge perspective, because as soon as we start to pump out the liquid, we'll have a lot of charge in the liquid. If we go over to a gas phase, then the charge goes down immediately as the density of the gas is so much lower. But the normal traditional system, that really brings us a lot of charge. The alternative here could be, of course, going over to a DX system, placing the condensers close to the evaporators. But that also means that we need to have a lot of ammonia in the spaces where we have the workers. And we don't really want that. We want it to keep it in the machine room, and that is why the indirect system is to prefer. In the indirect system, we use refrigerant to liquid evaporator, cooling down the secondary fluid, which pump out to the air coolers, the ice rink, whatever it can be, or we use a liquid to refrigerant condenser to heat up water, which we put to a cooling tower, or in this case, a dry cooler. Efficient system because the charge can be kept very low. The issue here is, of course, that we add additional step, we add a temperature increase somewhere here. And that is, of course, not really good for the overall efficiency. That means that the temperature approach in the heat exchanger becomes really critical. And with temperature approach, we mean the temperature difference between the leaving hot and evaporating temperature in the evaporator, and the condensing temperature and leaving hot temperature in the condenser. So here in the evaporator, we have a 2 Kelvin temperature approach, and in the condenser, it's a 1 Kelvin temperature approach. The higher the temperature approach, the worse the performance, but if we increase it, we get a better performance, better COP. I think that most people agree on this one. If we then go and have a look onto what the approach really means in terms of efficiency, we can take an example here, condensing at 35 degrees, evaporating at -10. Then we'll see compared to a system where we don't have any losses at all, the system with the 2 Kelvin temperature approach gives us a loss of approximately 6%. If we increase that temperature approach to 4 degrees, then we lose 13% instead. And then we can translate this one into what really matters, and that is the money. How much is someone going to pay for that extra temperature approach? Once again, we say that we have -10 evaporating, condensing at 35, estimating 5,000 hours of operating, 1,000 kilowatt. Well, then the extra money someone had to pay up is 15,000 euro. And I tell you that you can buy a lot of heat exchanger and a lot of very good temperature approach for 15,000 euros. Next question then is, how should we achieve this good temperature approach? If you ask someone from Alfa Laval, and I hope you do, you're welcome to our booth in Hall 6, then the answer will be a semi-welded plate heat exchanger or a fully stainless steel fusion bonded Alfa Nova plate heat exchanger. These square heat exchanger, they have the good thing with them that they are very, very thermally efficient, which means that we can go for a very low temperature approach. Preferably one would have an approach which is 0 or even negative. That might not sound possible, but actually with the condenser, you can get outlet temperature on the water which is higher than the condensation temperature by taking use of the hot discharge gases from the compressor. And that's perfectly possible in one of our semi-welded units. On the evaporator side, unfortunately, it's not possible to come to 0 approach or negative approach due to the forces of nature. We need to have a little bit of a driving force there. But I would say that as of today, it's quite standard that most people operates with the approach of 2 Kelvin. It's very much possible to get closer, to have an approach of 1.5. We can do that with our heat exchanger. The issue is that we would really see that the risk of having losses downstream in the system is so big that you actually loses the performance that you gain in the evaporators, and then it's not really worthwhile take the extra investment in the heat exchanger. Therefore, very often we have an approach of 2 degrees. The second main benefit with the semi-welded and plate heat exchanger is the low charge. If we look at the condenser connected to high pressure float switch, then we can see that we always drain the condenser. We don't have any liquid in it, more or less, just gas. As we said before, gas means a very low hold-up volume and thereby very low charge. In the evaporator, you will see that the only place we have liquid inside is basically the inlet port. As soon as we go up in the channel, we get more gas and therefore a very low charge. The only place we have really liquid ammonia here is in the auxiliary systems, in the liquid pipes, in the liquid droplets, and so on. And in order to really reduce this even more, Alfa Laval has come up with the U-turn separator, tailor-made really for semi-welded plate heat exchangers and plate heat exchangers as normal. A normal separator that is built on separating by volume. The U-turn, as you see, the smaller one down there, that is really built on the separation length and optimized for critical charge system. We don't want to hold up any volume there. We just want to let the ammonia go through. And thereby we are really reducing the charge to just the liquid column and the inlet port, reducing it a lot. The size, the two pictures you see here, the big one and the small one, that is exactly coming from the same installation, same temperatures, same capacities and so on, placed on an ice cream factory in Southeast Asia. And that is really the size difference you see between them. Another example of a U-turn installation, this is not an ice cream factory, but actually a heat exchanger factory. This is the factory in Lund where we produce our semi-welded and plate and frame heat exchanger. Here we take the energy from the hydraulic presses and turns it into hot water at 65 degrees, 826 kilowatts, using a U-turn and a plate and frame evaporator and a plate and frame condenser. This system now has been running trouble-free for more than 10 years actually, and the charge of it is only 40 kilos. And that's quite important for us because, as you can see, this installation is placed like 20 meters from where we have 600 people working in the office buildings, and then we are 150 meters away from where we have a residential area. So the charge for us is really important. And we see here that we have 40 kilos, which is well below this limit, where the Swedish agency says that the risk area is actually the machine room. And with that said, we can actually turn to some conclusions. First conclusion here might be that refrigerants, they are troublesome, avoid them. But as we are in Chilvent, I would say that, okay, just go ahead, but keep in mind that natural refrigerants has really worked in the long run. And in order to get it to work as possible, we should reduce the risk, keep the charge low, thereby use indirect system, because that gives us the lower charge. We place everything in the machine room and thereby reduces the risk. But in order to get the good performance out of this one, we need to keep the temperature approach low. And the best way of doing that is, of course, using a semi-welded plate heat exchanger or an Alfa Nova. With that, I thank you for listening and ask if there are any questions.